the fourth part. Well, this is, we talk more about kinematics, yeah, fluid kinematics. Well, we talk a lot about Mutex already. So this, the outline is, we talk classical fluid kinematics. We talk principal decomposition of the velocity gradient tensor, and we talk new fluid kinematics. We talk about some not very mature theory yet, but we talk about something, just the ideas and try and computation, right? Just the ideas. All of this is not matured yet. Yeah. So we next first talk the classical fluid kinematics. Well, classical. I think when we study the fluid dynamics, we first class is this Helmholtz decomposition. Helmholtz two parts. Well, besides the transition, so we have like this they called shear, then this they called rotation. Yeah, there's Helmholtz two parts, shear and rotation. Okay. Well, this is you can find the Helmholtz from wiki. You can find it. Two parts. This part is is the potential part. This part is the no diffusion, right? Not diffusion, not diffusion. No, where the flux is zero. That's flux free. So for this part, the two parts. Yeah, two parts. These parts we call them like rotational parts or something. This is called potential part. So, well, if we talk more theoretical, it is Cauchy-Stokes decomposition. This is Helmholtz, velocity decomposition. Deformation and rotation. And then if we go to Cauchy-Stokes, well, they symmetric and anti-symmetric. Symmetric is gradient of V and transpose. That's a plus. This is a minus. Anti-symmetric. A, they usually call the strain part. Yeah. Symmetric part. B, they call the rotational part, or anti-symmetric part. But unfortunately, this is a misunderstanding. For laminar flow, it's okay because we don't have rotation. Well, yeah, we don't have. Not for turbulent flow. When Mutex, we talk a lot about this, a lot about this. So that's the direction and this magnitude. The problem with the Cauchy-Stokes, the first, the vorticity cannot be represented. We call it anti-symmetric, and we talk rotating metrics, or we take vorticity. It's not rotation. So vorticity tensor really is a mixture of rigid rotation and non-rotation, anti-symmetric shear. So vorticity really has two parts. One is rotation, the other is anti-symmetric shear. Let's talk about that's the rotation part or anti-symmetric part. The symmetrical strain tensor is also a mixture of the symmetric shear, stretching, diagonal, off-diagonal elements, where they depend on coordinates, really. Because the symmetric shear including the diagonal element. The diagonal element is related to the coordinates. So the symmetric part really, it is a mixture of the stretching and symmetric shear. Well, the CS with the Cauchy stochastic composition is dependent on the selection of a coordinate system. And is therefore is not invariant. Because our decomposition shouldn't be changed when we change the coordinates. When we change coordinates. Well, for laminar flow, pretty much that's true, because the symmetric part, it is shear, it is shear. The non-symmetric part is vorticity, pretty much like vorticity. Well, this is shear, not rotation. Well, that's okay, because not rotation. Yeah, not for turbulent. Turbulent flow, you have rotation. You cannot use the anti-symmetric part. So that's a problem. That's what I say. So first, we need to select a unique system. When you cannot select a different system, then get a different answer. Then you get a different Cauchy stochastic, decomposition. You cannot do that. So we rotated. That's what I said. We rotated. Yeah, this. That's what I said. We use Q1, Q2, and all as mutex. We use the mutex, rotated the originally full matrix to become this format. That's the use the mutex as one of the axis. So this we call a P rotation. P rotation just rotated this Z parallel to R. We rotated Z parallel to R. Okay? Also, this is we call a P rotation. But that's not good enough. We need a second rotation. We make what? When we get this, we need a second rotation, make nominal CI equal to nominal CI, the diagonal element. This we call the Q rotation. No, that's wrong, that's misleading, not P rotation. Q rotation, this. First one is, sorry. This should be Q rotation. I don't. Yeah, I cannot check now. I must come back. So the Q rotation just make the diagonal element equal to each other. Then this is unique. This is unique. We want to get unique coordinates. You can get different coordinates. Get different. Each point, different decomposition. When we get that, then it's easy to do the decomposition. We call the rotation, stretching, and shear. Rotation, stretching, and shear. We call R, S, C, and S. This is we call. Well, if we use the, T, we use the T, so we get this. That's the low triangle. Same thing, but it's transpose. Well, transpose. This is what we use. Well, this apparently, 3 parts is different from Cauchy stochastic. Cauchy stochastic is 2 parts. None of us similar or same as Cauchy stochastic. First, rotation, Cauchy stochastic doesn't have. Second, this stretching and compression is fixed. Fixed, it's not changed. You cannot change it because lambda CR is lambda CR. It's never changed. The eigenvalue. You cannot change the eigenvalue, no matter how rotated coordinates. This is invariant. The shear is non-symmetric. In the Navier equation and the Cauchy-Stokes Helmholtz, this part, it is symmetric. This is not symmetric. This is non-symmetric. So this is three parts. I think some people, quite a number of people do the theoretical work. They call it triple decomposition. The triple. This really is a new text-based triple decomposition, or my decomposition. They didn't say that. They just say the triple decomposition. They didn't say who gave the triple decomposition. What is my group given? Be careful. The original is. Well, I see quite a number of people use this triple decomposition. Well, this is totally different from Cauchy-Stokes. Okay? So then we talk about new fluid kinematics. What means your fluid kinematics? Well, fluid kinematics only define, there's a shear, strain, or something like that. So we do the P rotation, make it is parallel to the P rotation. Three parts: R rotation, S rotation, SC stretching. Then we do the P rotation and the Q rotation. We need to come back. This is a come back. Come back to originally small x, y, z. Okay? We need to come back. Well, because we do the P rotation, we do the Q rotation, we need to come back. In the x, y, z, small x, y, z. Small x, y, z system, we get R, S, and SC. The three parts. In originally coordinates. Well, assume we get a QP already. That's the new text. There's another two vector. We say the orthogonal. The three vertex orthogonal. And we use the PQ to the new text. It should be 0, 0, 1. That's parallel to Z. Is the Z direction. So that means the new text uses this transpose. Then we get a new text, as I say. Okay. So therefore, you see, del V is the gradient of vorticity, of velocity. Velocity gradient tensor. It is decomposed into three parts: R, S, shear, SC, stretching, shear, and rotation. Come back to the originally coordinates. We call the R tilde, S tilde, SC tilde. This is to any coordinates. Three parts. Okay? Well, for R, it doesn't matter. We just rotate it. But this is all in the principal coordinates. We cannot use principal coordinates. Why? Because each point has one, principal coordinate. Each point. Then different point have different coordinates. So you cannot take derivatives. You cannot do that. We must come back to originally small x, y, z. We must come back. So does all come back? All come back become this. Or there's a new text. This is a component in the z direction. This is a component in the y direction. Z direction, y direction, x direction. This is the rotation pattern. Come back to the original system. This part we call rotation. Any question? We use the principle, we make a decomposition. We need to come back to the origin. That's the idea. We need to come back, but you cannot use different coordinates. You get different, decomposition. That's unique. It cannot be, any value. No, that's unique. We need to come back to the original, coordinates, get a unique decomposition. That's the SC. SC is that we also need PQ come back. Well, we can see that. How to do the compact P and Q and what do we do? We see what happened. That's the stretching. That's I said maybe in the solid mechanics or the tensor decomposition. They say, well, your diagonal element can be transferred to shear. No, not in the turbulent case. Turbulent have vortex. Vortex is fixed coordinates, fixed axial. You cannot say you cannot. So when we go back, so what do you see? You see that? Lambda CR, that's identity. This part is identity. This part is additional part by Nutex. Well, vortex you have axial. You have axial. This axial causes some trouble. This axial create some force. Don't forget that. Don't forget, they create some force. Well, the idea is idea. Well, and this term is what? It says stretching. This term really like pressure. Like pressure, you see? That's identity. But this term is what? This totally caused by the Nutex. Well, originally, but I have no proof, as I said. I just talk about idea. Originally, I saw that this is the turbulence perturbation or disturbance. Original, say, caused by Nutex. Original, I say. Original, I say. That's the source of the noise. You see, this is noise, this is identity. Any direction the same. This is not. This is apparently related to Nutex. Okay? So that's the part. And the second part, the stretching and the compression is not required. It's not required. This is required. The identity. They same, all directions same. This is not. This is not. This could be the source of the noise or the perturbation. The last part, it is shear. That's the shear. Well, it's quite long, but what I do is very simple. I just use the original one, this original one, minus rotation part, and minus stretching part. Well, what do we get is this. So, this is our new fluid kinematics. Instead of Cauchy-Stokes, symmetrical and asymmetrical. This is not. This rotation, shear, and stretching. 3 parts for vortex. If no vortex, you don't need to do that. No vortex, Nutex 0, then what happened? Then what happened? This is 0. This is a part of pressure, you know. So if you're not, you don't have that. That's what I said. You don't need to worry about that. Cauchy-Stokes may be good enough. You see that this 0, rotation 0, well, you don't need to worry about that. And then stretching, you don't need to worry about 0. Okay, so you only need to worry about this. Well, this is 0, and this is quiet. This is 0. It didn't do anything. Origin, yeah. So we don't need to worry about it. If no vortex, we don't need a triple decomposition. When we have vortex, we cannot use Cauchy-Stokes or Helmholtz decomposition. We cannot. Vorticity decomposition. Yeah, we know that the vorticity, we can have 2 parts. So if we start any DL, you will get DL cross product of the all mutex and the cross product of S. Well, this for any DL. This stands for any DL. So what the conclusion? That's the vorticity or your cross product, yeah, or we call Q of equal to R plus S. This is exactly formula, mathematical formula, vector, 2 parts, rotation and shear. This is exactly. You don't need to suspicious. No need to, So, therefore, this also tells you vorticity is not a rotation, not a vortex. It could be only when what? S is 0. When S is 0 or shear is small or 0, then vorticity, it is vortex only. This formula is mathematical formula. It's through the mathematical definition. It cannot be wrong. Cannot be wrong. Well, no matter you want to, I don't want to. Some people don't want. I don't want. I trust book. I don't want to listen to your talk. This is mathematical relation without question. Well, if we don't have, you have suspicious, so you give me the question, challenge. You understand what I'm saying? Well, some people don't like it, they don't want to. I don't know. What is it is what is it? Fluid rotation, there's no question. We don't need to talk about it. We don't need to. Well, this is mathematical. What is it? It is vortex. If and only if shear is 0. If and only if. Yes. Yeah.
B is anti-symmetric.
Beta is equal to this. B is the anti-symmetric. Anti-symmetric.
Curl B plus S is not anti-symmetric.
It's anti-symmetric. Yeah, you see? Yeah.
S.
Which one?
S. Shear.
Shear is not. Shear is anti-symmetric, right?
Then I want to know how non-anti-symmetric S come out from anti-symmetric B.
Yeah, this part is vector. This is vector, yeah. But this is the matrix. That's anti-symmetric. This is anti-symmetric and anti-symmetric. Both anti-symmetric.
Then by taking the dot product with DL.
Yeah, DL is any line.
Yes. Then I just want to know.
Yeah.
Originally anti-symmetric. And that curl B.
B is anti-symmetric. Yeah.
But it ends up with non-anti-symmetric S.
S, what's S? S is anti-symmetric. No, S is anti-symmetric.
It comes from the anti-symmetric.
Yeah, both S are antisymmetric.
How antisymmetric one
Yeah, this antisymmetric 1, the antisymmetric 2.
becomes non-antisymmetric S?
No. S is, sorry about that. This is going to get confusing. This S is not different from other S. S. Sorry about that. Yeah. Well, now I know your question. Originally, I talk about S, right? S is here. I know what your question is. This S, sorry about it. This maybe I didn't say clearly. Yeah, this R, I think this is S. This S, it is not antisymmetric. That's correct. Yeah, but here we talk about S. Here, this S is this S, antisymmetric. It's different. Yeah, maybe I didn't explain clearly. Yeah, it's different from the triple decomposition. The triple decomposition S is not antisymmetric. Here, S is a traditional S, antisymmetric. Yeah, that doesn't mean I didn't say clearly, so it caused some confusing, right? Yeah. This S, it is antisymmetric. R is antisymmetric. Yeah. Well, it's not different from the S, but I need to, make some notes. Say this S is not previous S. Previous is symmetric plus antisymmetric. Yeah. But this is, yeah. Well, we look at the graphic. Yeah, this is vorticity. That's on the vortex ring. This is on the leg. This leg, we say that's the vorticity. We say this nutex. This is shear. You see, vorticity is what? Can you say vorticity is rotation? Can you say vorticity is vortex? Well, apparently it's not. That's the vortex. This is shear. So in the nominal vortex leg, vorticity almost shear. Very small part, very small part is rotation. Where for the ring, well, it's a little bit better, but still major part is shear, and small part is rotation. Well, this is from DNS. From DNS. So that's what I say. Come DNS. I don't think we have argument with that. Well, there could be some argument. Your DNS is correct or not correct, accurate or not accurate. There could be. But as I said, what's wrong? Huh? This is no question about that. Well, of course, there's a misunderstanding. This S is not the previous S. Yeah. This is antisymmetric S. Okay? And we say, well, this is exactly correct. Well, we could do another, we call it R and NR decomposition. This is also, not a triple decomposition, two, decomposition. This part just take the rotation part out, and non-rotation. Now, what is meaningful? Well, only turbulence, we talk about rotation. Vortex, you have vortex. If you don't have vortex, zero, nothing changed. Well, there's nothing changed. Yeah. That's the long rotation part, the rotation part. Only for vortex points. Only for. This another, well, the decomposition have many different ways. So we have triple decomposition, and this is rotated and non-rotated. Okay? Yes.
For non-rotating phase,
What?
for non-rotating phase,
Yeah.
these three items on the axis in general should be
Well, here we talk is still rotation point. We take, well, as you said, if no rotation, we have real eigenvalue. I know that you guys published some paper. I've been Chen Xi also published a paper. Yeah, that's for the, well, not for this is the rotation point.
the non-R
Rigid rotation.
NR.
Rn is rested part. This is still in the principal coordinates. Still, yeah.
Non-rotational points.
Yeah.
Just for rotational points.
For rotating point, it has two parts, two decompositions. Yeah. Still rotating point. That's not three eigenvalues. Not that case. Three eigenvalues more complicated, I think. Yeah. Well, that's you can use now with three equations. Yeah, three real eigenvalues. Yeah. That's not the case. That's here is still one.
Why in the diagonal you have two eigenvalues equal to each other?
Well, that's the principle. That's our principle. We call it coordinates. In our principal coordinate, because we need a unique. We need a unique. Unique is make this equal to each other. Otherwise, you have too many.
It's non-rotating, you don't have principle.
Well, no. This is still, we suppose it's still vertical part. We still use principal coordinates. Did you see that? In principal coordinates, we just divide the two parts.
The point is how you define principle without a rotation.
No, that's the problem. That's not, we didn't mention this. This is more difficult. I know that you guys published a paper, and Chen Xi published another paper. I think, yeah. Chen Xi introduced a new concept they call resistance. He will talk about it tomorrow. He just introduced, the other concept. Yeah, I know that you use the three eigenvalue and three eigenvector. They use that. But your problem, I think, you may be correct, maybe not correct. You use the three eigenvector, they are not orthogonal. Yeah, that's the problem. Yeah, three eigenvalue, three eigenvectors, they are not orthogonal. But Chen Xi introduced is, three eigenvalue and three orthogonal. Well, usually if the coordinates is not orthogonal, well, the components is very complicated. I think it's not easy like orthogonal. If not orthogonal, like lambda ci, they not orthogonal. We usually, in whole this system, we always use orthogonal system. Orthogonal coordinates, we always use coordinate. Well, you can use non-orthogonal. That's complicated, very complicated. It's not simple, easy, like a projection, something like that. It's not. I think for IJK, so for IJK, it's not orthogonal. It's easier. You say, V equal V I, well, U or U plus V J plus WK. That's easy. If it is non-orthogonal, that's much more complicated. You cannot use this. You cannot use three projections. This U is a projection, Vi, the V projection in the J. But if non-orthogonal, you can use this very simple relation. You cannot use it. Yeah, it's much more complicated. You just cannot use a projection. It's not equal to each other. I don't think it's very equal to each other. Because U is how to get a U. it is V dot I. If it's non-orthogonal, you cannot do that. So that's why we use the orthogonal. Yeah. But you can use non-orthogonal. That's make it much more complicated. That's what I say, yeah. Well, this is just to say, I give the name because I'm in UTA. I just say, well, there's a UTA rotated and non-rotated. Well, because non-rotated, you still can use Stokes assumption, not for the rotation part. Rotation part, you cannot use, Stokes assumption. That's what I think. Now, I talk about divergence of a tensor. That's what we talk after lunch. I just say, well, here, because the Stokes, they assume the strain and the stress is symmetric. Nonsense about an anti-symmetric strain on stress. Unfortunately, this misunderstanding. The shear can be symmetric, can be non-symmetric, can be anti-symmetric, can be symmetric. No, look at it. This is mathematics. This is mathematics. I'll never see that. So we take a definition of this gradient transpose. Right? This transpose, we take divergence. Then we take the transpose again. So we do step by step, okay? Step by step. Step by step. So what do we get at? We get a 0. Or we get a trace, we get this one. Well, I just ignore this step. So you can find this step. This is mathematics. So we find what? This is in a trace. The trace is pretty much a compressibility. For incompressible, this is 0. What do we find? That's gradient of T, gradient of V of T, the transpose. The divergence is 0 for incompressible. It is trace, gradient of trace for the compressible flow. What is mathematics? This is nothing with physics or with fluid dynamics or with the Navier equations. There's nothing. This is 0. Okay, therefore, you see, we use the Navier equation. We use this with custom, okay, equal to this. And then we use my equation. It's anti-symmetric. This vorticity, this strain, they're same. The divergence is same. Or in other words, the force are same. So, the Stokes conclusion say the stress and the strain must be symmetric, cannot be anti-symmetric. My conclusion is the stress and the strain is anti-symmetric, cannot be symmetric. They get the same results. This is mathematics. You can derive this. You can derive this. It's mathematics. There's no question about that. So who is correct? The Stokes say we must, that's a strain, and the strain must be symmetric. But I say they must be anti-symmetric. But the real case is what? Either symmetric, either anti-symmetric, either combination of symmetric and anti-symmetric are correct. They're all correct. Well, what's wrong with that? Then what's wrong with that? We talked to Professor Xu, what's wrong with that? There's one serious misunderstanding. One serious misunderstanding is what? It is a momentum theory. Conservation of moment of momentum, right? Theory. We have such a law, right? This is not true to fluids. We know that the mass conservation is true. The momentum conservation is true. The energy conservation is true. The momentum conservation is wrong. Why? Why? We don't talk about the solid mechanics. We talk about fluids. Let me give examples. We know we cannot use hand. We cannot use hand if this is a screw, very tightened. How to do that? We use tools, right? We use tools. It's easy to take this screw out, right? The reason why, because the momentum, right, is larger. You get a force, right? Also times what? Times L, right? Yeah. It is very large. It is very large. But my question is, the fluid is still. The fluid is consist by steel, but this is steel. This is steel. That's iron. The fluid is steel. So the momentum and the conservation of momentum does not exist. Does not exist, but they use it. They say, if you have, so if you have this non-symmetric, right? A non-symmetric, so they will rotate it, right? If you have this part, then rotate it. This rotation, according to momentum, conservation of momentum, it is zero, while the force. So there's a high order, equal order. So the conclusion, it is stress and strain must be symmetric. That is the conclusion, based on the conservation of momentum. But this law, or this is not exist more unless our fluids is made by steel. Who can make that? Who can make that? Who can make? This is this iron, the steel, fluids. This is fluids. So you understand what I'm saying? So their conclusion is based conservation of momentum. Unfortunately, it does not exist. That's also in the book, in many books. They say your rotation is high order, so it is zero. So the conclusion is partial, they must be the same. This is just say, and then this is what? Well, I think this is maybe, this must be symmetric. That's what the conclusion says. They cannot have anti-symmetric. If anasymmetric, they will rotate. But rotated could be ignored. So the conclusion is stress and strain must be symmetric. But what do I do? But what do I do here? I just say what I do. See that? The strain is symmetric. I say I use vorticity and asymmetric. Same conclusion. This is force. There dot there we. It is force. It's the same. So you use the symmetric force or use anasymmetric force. It is same. It is same. The mathematically, you don't need a suspicious. You don't need to be suspicious. Now think about that. Think about that. This is mathematics. You can check that. Yeah. So well, it doesn't mean I blame the previous generations. It doesn't mean, well, why they don't have anything? They don't have a computer, they don't have instruments. They give some assumption. That's understandable, but it's not truth. These misunderstandings. It's not truth. So what I do, I don't use Navier-Stokes equation. I use my equation, same results. Don't need suspicion. What's the question? Yeah.
Then what you say is if you put anti-symmetric tensor into constitutive equation, what will happen?
Same results. Same, yeah, same. Because this term is zero. For incompressible, it's zero. This is zero, yeah. When you use this term, right? This term is zero. You positive, you plus or minus the same, because this term is zero.
So how you write a constitutive relation?
Oh, constitutive is another issue that should be related to the gradient of velocity. The gradient of velocity, they don't use it. Navier-Stokes, they don't use it. They just use stress and strain. They're symmetric. But I use vorticity, the same. The result is the same. Why is the same? This is zero. Well, for incompressible. For compressible, this is another issue, another term, the trace. Okay? So if you don't believe, you can repeat that work. This is mathematics. Well, thus I said, why they create this misunderstanding? They say strain and stress must be symmetric. Why? Because they use momentum theory. We cannot use this for fluids. We cannot. They prove it's wrong. It is wrong. Well, you can find it from the fluid dynamics textbook.
Then basically what you say is angular momentum conservation do not need to be applied to fluid.
We don't have that. We don't have the, yeah.
Do we need to conserve angular momentum?
We don't have that law. We don't need it. Well, for Navier-Stokes equation, they don't have that equation. They don't have addition. Because you don't have addition unknown. You don't need that. But you can, they try to prove that additional. They say, why is it symmetrical? Because the conservation of the momentum, yes, yeah.
Their explanation is they already implicit.
Yeah, they just prove that. I just want to prove that. Why stress is symmetric?
What you say is you do not need this.
What is wrong? What is wrong? The stress and the strain could be symmetric, could be anasymmetric. It's the same thing. Could be mixed. Well, when you get the same thing, you can mix it. You can say we use two over three strain and 1 over 3. What is it? Same. You don't believe, you can test your equations. If you have DNS code, you can test it. You can use what is it, or use the strain. Then you say I want to use 2 or 3, 2/3. You can use that. Then 1/3. You know what is it? It's up to you. It's the same. That's strange. That's the same. Yeah. Well, that's our new equations. Oh, that's original equations. That's my new equations. That's my new equations. Well, no, this is nothing new. That's nothing new. That's not like a new text. And this is not groundbreaking or no. I just say this is just clarify people misunderstanding. Well, this is the original equation. This is a new equation given by me. What is it? That's strain and stress. They mathematical, they exactly the same. Numerical, they exactly the same. Well, I just want to correct the misunderstanding. Because some people say, well, the strain must be symmetric. It cannot be anti-symmetric. They told me many times. Some readers tell me, yeah. I still didn't reply that. Yeah, I published this paper, they have the questions, and they prove I'm wrong. But I just don't have time to reply yet. Well, that cannot be wrong. That's a new equation. Well, this is still Navier equation, just different format. Well, not Navier because this is not given by Navier or Stokes, given by me. So we cannot call this Navier equation. But the same, mathematical, exactly the same. If we don't believe, use it. Okay? Then of course, what's the advantage? Well, use this, what's the advantage? Well, you can need to advantage. How to say? Because vorticity is anti-symmetric. They only have 3 unknowns. Strain has 6 unknowns. Strain has 6 unknowns. Vorticity is 3 unknowns. Because the diagonal is 0. Diagonal is 0. Well, we can say, you may, you may save some time. May. I don't know. The results I tell you, exact same. You don't count, you can have any change. Yeah. You see? Well, if you don't mind, you can try to your DNS code. You see any difference? Well, the possibly good is 3 unknowns here. Strain 6 unknowns. 6 and 9 because symmetric, they have 6. Anti-symmetric, they 9. But 3 zeros, 3 anti-symmetric. Okay? What does the vorticity-based governing equations? Okay. Yeah, because for the incompressible, it's 0. 0. And this is mathematical trick. Well, we cannot get the conclusion. Stress must be symmetric. We cannot get a conclusion. We must follow the conservation of a moment. We cannot. We don't have such a conservation. Well, that's just repeated. I don't think there's anything wrong. Well, you can change that. The reason is this 0. Okay, strain is symmetric. Stress is proportional to strain. The Navier example. Both strain and stress are symmetric. there is no rule of vorticity. Does not with three equations say that. Well, what's the new equation? There is a stress is proportional to vorticity. That's just a different answer. Both vorticity and stress are asymmetric. There is no rule for strain. No rule. This is just the opposite. No rule. Only rule is vorticity. If we don't believe, test that. Test that. Yeah. That's just opposite. Yeah. Yeah. Got a question? Yeah.
About number four, there is no rule of vorticity that actually viscous terms can be expressed by rotation vector. So I think the rule of vorticity vector exists in Navier.
Well, in Navier three equation, so help. Yeah. There's no vorticity. I don't think help. There's no vorticity. That's the Navier three equations. There's no vorticity. Vorticity, it doesn't matter. Well, you have vorticity, but it doesn't just play a role in the Navier three equations. You don't have any role in the Navier three equations. My equation, it just says there's no rule for the stress. We don't need the stress. We just only need the vorticity. It is a mathematical game. It is a mathematical game. But it isn't really trivial, not very important. Well, from the equation, you say, only rho is the stress. For in my equation, it's only rho is the vorticity. Not room, not seat for stress. Not seat, you have no seat, no rules. Well, rotation, of course, we have, but that's the same. Not rotation, no vorticity. Rotation is a different story. This is not vorticity. So this is not vorticity. P is not vorticity. Rho is not vorticity. VV is not vorticity. As I said, in Navier three equations, vorticity didn't play any role. For my new equation, I just say, sorry, stress, please leave. We don't need you. We only need a vorticity. Yeah, you answer, well, this is a mathematical game. The results same, the equation same, there's nothing changed. That's what I say, there's nothing changed. But maybe have some advantage. It is 3 unknowns, is 6 unknowns. Yes?
The nonlinear term,
Yeah?
you can write it in terms of vorticity, right?
No. Still use V. We didn't use vorticity.
It would be
Yeah, well, you can, but yeah, more complicated.
vorticity cross velocity.
Yes, well, you have to use a cross product, something
in
like that.
both equations.
Well, then you change the right-hand side as well. Yeah, does become vorticity
In the
equation.
top is also there. In the original one.
Vorticity-based new.
It's in the nonlinear term.
Well, I didn't change the nonlinear term. I just changed the force term, the surface force term. I didn't change the nonlinear term. Just change the surface force. Yeah. But the surface force could be symmetric, could be anti-symmetric, could be. We don't know. Yeah. Well, this doesn't mean over 10, now it's 3 equations. They're same, actually. They're same. If we don't believe, we can test it. Then we give the exact. Well, I just don't want to talk much about that. So we tested by the back step flow, and for the turbulent with the vans, there is the same results. You see, almost same results. That's we tested by different. Yeah, we tested the duct and used 2 equations. They almost the same results. Almost, well, it's numerical anyway. Yes.
Can you go back to slide?
Yeah.
Back to slide.
This one. Next.
Last one,
This one, yeah.
So this original and the new, if you add that up, then basically you can see just the velocity gradient is your.
Yeah, well, there's nothing changed. It's the same.
I mean, this is the right-hand side is anti-symmetric.
Yeah. The top is symmetric.
Then if you add them up, your rule becomes.
Right. If we add them together, this cancel. Right. The really they related is to the gradient of velocity. Real is that. You cannot say it's only related to stress. Well, you can. It's correct. You can. But it's not physics. Physics is you only can relate it to gradient of velocity.
No. If you relate it to velocity gradient, that means you add in your constitutive relation.
Right. That's,
originally, it should be.
well, this is a constitutive, yeah. But this is Stokes.
No, originally there's no velocity gradient.
Right. That's Stokes assumption. That's Stokes assumption, yeah. There is related to stress.
Related to stress.
Right.
There's no assumption at all.
A law assumption. Okay.
The stress term.
No, stress is a strain. That's not stress, that's a strain. Well, when you put the mu here, that's a
originally, if
Yeah.
you do not include your friction coefficient, originally there should be a stress term component there.
Well, the stress is, you cannot write this way. This way also including the,
Stress tensor.
well, that's the strain tensor, not the stress tensor. The strain, original stress tensor law assumption, that you are correct.
Yeah.
But well, when you from stress to strain, that's is the constitutive. The constitutive, they say is proportional to stress, to strain, to strain.
In this case,
Yeah,
proportion
to
velocity
strain,
gradient.
strain. Yeah. Well, the action is to the velocity gradient. The Stokes say, I say, and we combine them. This is the.
The rest is
That's the velocity gradient tensor. That's correct. Yeah. So that's real understanding. You understand? Yeah. Well, I just don't want the book, textbook misleading the people for 100 years. I don't want to. They continue to misleading the students. I don't want to. As I said, well, I give just the, example. So, strain, yes. What is it? Yes. Combine together with the gradient, yes. 3 yes. 3 yes. Okay? Well, this is, we check that. I come back, you talk constitutive. Constitutive, yeah. Well, now we have 3, as I said, decomposition. We have 3 parts: rotation, stretching, and shear. How do we know we should use mu, viscosity? It doesn't make much sense to me. So you understand that? How to know? We never prove. We only do the exam, do the experiment. So when V is larger, F is larger. According to this, because we assume F is mu partial U partial Y. Then we measure the F, measure this, then we get a mu. This is physics. It doesn't give anything about the rotation. It doesn't give anything about the stretching. How do you know it's mu? How do you know that? You have questions as well. You have questions as well. We have questions as well. I published this paper a long time ago, I think. Yeah. That could be mu1, mu2, mu3, mu4, who knows? but we didn't measure that. We didn't measure. Rotation, what's the rotation, mu? You know, what is the mu for rotation? What is for the stretching? Why mu same? And that's assume mu is isotropic. That's mu is isotropic. Who knows mu is isotropic? Who knows? How do you know? You have rotation. Why mu is isotropic? Nobody knows. So that's why I ask my student to derive the matrix equation. The matrix equation maybe give more reasonable answer. This is not reasonable. How do we know mu? Mu is constant. You only do the experiment like this. This is shear. How do you know rotation is the same? How do you know the stretching is the same? Nobody knows. This is just a guess. So that's the idea. That's not a theory. not theory, yeah, that's the idea. This is Dr. Miss Chen Xima. He's tried to develop the matrix equation for fluid dynamics. Metric equation. What is metric? Everything is matrix. You know, it is not just a vector, not a scalar, not a vector. This is a matrix. Because the mutex is related to matrix. Mutex is not just related to vector. Well, that's here we will talk more tomorrow. Talk more about that. This is matrix equations. I think this is where we are making more sense about the mu. Mu. Why the mu is constant? That makes no sense to me. Why mu? It's not. It doesn't make no sense to me. That's what I say. Well, this u is not u. U is matrix. Where is u? Or u is here. U is matrix. The capital U is matrix. Okay? P is matrix. Now, he already tested this 2D problem. The 2D problem gives the exact same answer. Well, we try. We didn't get finished yet, not finished yet. What I think, because we want to develop new tech dynamics, but new tech is not differentiable in the coordinates. No, I don't think they're differentiable. So, but it could be differentiable in the matrix form. Could be. That's what I think. Well, I didn't say about. Well, this is a DNS, something like that. Then I talk about it, where it's not realistic to do DNS for everything. It's not. Pretty much we do the Nagy dissemination, most cases. Or even runs. Well, runs is supposed we have steady flow. Unsteady runs, it doesn't make much sense, I think. Right? Yeah, that doesn't make much sense. So pretty much we do the LNES. The LNES will have addition term. Well, Dr. Yu will talk about addition term, how to deal with addition term. They call it SGS model. Some people have 6 terms, they call it real stress. Right? Real stress and SGS model, anyway, you change the equations. You change governing equations. Anyway, well, when you change the governing equation, there's more trouble, more questions. Yeah. How do you know your N is north part is constant? How do you know that? It's just a change in the viscosity. They call it eddy viscosity. Eddy viscosity First, what is eddy? What eddy? That's what I say. What is eddy? Well, eddy is a new text. New text is a vector. How to change the mu? How to change that? How we just say we need one term. Originally is mu. For example, like partial u, partial x, partial u, something like that. Partial, well, they may be partial square u, partial square u, partial y square, right? Yeah. And partial square u, partial z square. Something like that. And then, well, like a partial u, partial y. Well, if they talk about the tau, xy, equal to mu, partial u, partial y, plus partial v, partial x, maybe 1/2 here. So, so now they say, oh, turbulent flow. Or you have subgrid. So now you have 1/2 mu plus mu t. That's very famous. Well, they maybe have like 1/3. 1/3 is right. UII maybe have not so. Well, this we only change this. They call eddy viscosity. Well, that's I said. That's general two questions. That's general two questions. First question is eddy. What is eddy? Eddy is a new text. Why become a number? It doesn't make sense. Second, your term, your lost term, I think it is that one, right? It is like UV or something like that. UV, right? Then you take a filter or something like that. UV. Yes, something like that. This is the term you lost. You may use the U prime, V prime, then take this. This is a convection term, nonlinear. How nonlinear become linear? That's another question. And then you have the question, why the viscosity changed? Why the viscosity is from here? From this experiment, how they can change it? Well, all of these questions, I don't think they can answer. We need to answer. We try. But we cannot say, yes.
You're saying the U prime, V prime.
Yeah.
Remember the first eddy viscosity concept was given by Boussinesq.
Yeah, Boussinesq, yeah.
And the Boussinesq only give that eddy viscosity model to the U prime, V prime component.
Right.
Right?
Right.
So in that sense, that means the eddy viscosity model can only model the shear stress.
So U prime, V prime. No, even U prime, they cannot. One is non-linear term, how the linear term?
The really problem is U prime, U prime.
Oh, okay.
We don't have that model at all.
Well, we have. We
consider
have.
U prime,
Yeah.
it has always been positive, right?
Yes, yes.
So if it is positive, if you correlate it with velocity,
Mu t will increase.
and your eddy viscosity more likely become both positive and negative.
It could be. Yeah.
Right?
Yeah.
Negative is violate the
Physics.
right?
Yeah.
So that's the logic.
Well, there's a lot of problems. I agree. But the Boussinesq assumption is no scientific foundation. No science. That's just engineering assumption. Yeah, the engineering assumption. Yeah, it's not physical.
It is just for
Yeah, just for engineering. Yeah, guess. Yeah, I think. I don't think they have any, scientific foundation. I don't think they have. Why we need a Boussinesq assumption? Why we need that? We have no reason. Well, people think that for engineer application or you fast speed, a low speed, because vortex, you mix them, so high speed become lower, low speed be higher. That's similar to viscosity.
That viscosity has a more, I believe that was quantum mixing length.
Ponto is first use the mixed length, yeah.
Give the reason to express that.
Yes, he used the Bose-Niski assumption. Use the mixed length, yeah. But this is engineering anyway. This is engineering. All of this are engineering assumption. There's nothing to do with the scientific foundation. Scientific is no foundation. How the non-linear term become linear term? How to do that? That's what we say. The non-linear term, U is sine x. For example, that's the U prime, right? U prime equal to negative cosine, the cosine x. So U prime, for example, then become sine x, cosine x equal to 2 sine x, sine 1/2 sine 2x. Well, you change the frequencies. But viscosity cannot change the frequencies. Linear cannot change frequencies. The nonlinear increase in the frequencies.
The added viscosity is a function of velocity, then you can change.
Well, unless, but
Viscosity is a function of velocity, then it becomes.
that could possible, yeah, right. But they have a lot of problems. Why does the linear term have there's also why they isotropic? Why they are a constant? All of this. Well, Doctor, you will talk more about this. I think he will talk more about this. But anyway, this I believe this SGS model have no scientific foundation. Even we say eddy viscosity. What is eddy? What eddy means? Eddy means vortex, rotated. Rotated have direction. This vector, how become the scalar? It doesn't make no sense to me, sounds to me. Well, I just tried, we almost at the time. So the conclusion is that velocity gradient tensor is unique, but the corresponding matrix number is infinity. Well, that's to say, this is physics, this is the mathematics, and this is not unique. We need a unique coordinates. We call it principle. That's why you ask me, why lambda CI equal to lambda CI? We need a unique. We cannot talk in the different coordinates. We cannot. So we say we need a principal matrix or principal coordinates. Then principal decomposition is unique. That's unique. Rotation, stretching, and shear. Principal decomposition can be done in the original. We need to come back to the original Cartesian coordinates in the new fluid kinetics, because we just cannot do this in the principle. Principle, each point have different system. We cannot. We must come back to the original. Stress calculated by velocity gradient and strain or vorticity is equivalent. That's what I said. Well, stress is unique. We don't have any assumption. But when we talk about stress, we use a constitutive something like relation. Yeah, that's the problem. You use the strain or use the vorticity. They're same. Or use the gradient of the velocity. They're same. Mathematically, they're equivalent. Okay? Stress calculated by velocity, gradient strain or vorticity are equivalent. The three things are equivalent. And by velocity gradient, by strain, and by vorticity, they're the same. Okay? Velocity gradient has 9 elements. Strain has 6. But vorticity only have 3. So which one you want to use? They're same results. Okay? Either one you use. Well, now we Stukas 6. Use my new one, 3. So which one you will use? If you don't mind the computation time, why just use the vorticity gradient? Now we Stukas save 9 to 6. I save 6 to 3. Well, it is up to you. Well, anyway, this is not a groundbreaking work. That's it. This is just a game. The new governing equation by vorticity is Galilean invariant, simpler and with a clearly physical meaning. Well, that's we use the vorticity. Why vorticity? It is better, but vorticity can be decomposed as mutex and anti-symmetric shear. Anti-symmetric shear. The new governing equations has a vorticity, don't have, which can be further decomposed, rigid rotation, pure anti-symmetric shear. The new idea, maybe, I don't think this is really serious or important, I don't know, for turbulent research. This is just clarify some textbook misunderstandings. They say, well, stress and strain is symmetric. Stress must be symmetric. That's not true. That's not true. Yeah. Well, that's a reference. We actually publish, but I never say this is very important. Thank you. Any questions? Any questions? So you ask. My part is.
The bus is waiting at the same place that the bus dropped you today.
Okay.
So
It's outside the building, right?
no, it's because there is.
Oh, they cannot park in. Okay.
So it's maybe not much time for the.
Okay. So ready. You know, bring all the stuff. We don't have much time to discuss. Bring your stuff. Make sure empty the room, and we'll capture the bus. Yeah. So we are done for today. We are done for today. Well, tomorrow we have more presentations about the new governing equation and subgrid model and new methods or something like that, and practice. Okay? So thank you for your patience. So see you. Yeah.